right away. But we're gonna do the conference picture downstairs. And now it's a big pleasure to introduce Ezgi Kantarcı Oğuz.
Thank you.
From Galatasaray University. And she's gonna tell us about the reactive process and passive expansion.
Yes.
Please.
Thank you for the invitation. So it's going to be quite close to what Esther was talking about in some sense. Then we'll be talking about cluster algebras, but first I wanted to talk a bit about the combinatorial objects, the model I'm using. And this is about border ideals of posets. I think some of you might be familiar with it if you are not. It's a different definition for an ideal than in most algebraic structures. So for posets, we'll generally talk about transposets, which are mixed by compositions. So this is a one poset, one step up and one step down. So relation-wise, this W2 is larger than or equal to W1 and W3, which are no relation. And for this particular project, we also have the two-row versions of these. So we have twice the number of nodes. And when we are talking about ideals, we are talking about subsets of these nodes that are down-closed. So if you include anything, you need to include anything under it and connected to it. Let's look at this one. So we can have an empty ideal. We always have that. And we have the singles W1 and W3, but we don't have W2 because it's not down-closed. We have the pair W1 and W3, and then we have O3. And we can think of these as monomials and sum them up. Get the weight polynomial or the poset one. We can think of it as a kind of generating polynomial of the ideals. And if you have a more complicated poset, you'll have more ideals. But it's the same process. And we again get a weight polynomial. So this is mainly going to be the combinatorial structure we'll be using. And we'll have a shortcut of calculating these polynomials from the posets. This using matrix multiplications. So now we have a very, very brief introduction to the cluster algebras, which is going to be going over some of the things that we talked about. So in a cluster algebra, we have cluster variables that are a set of generators, and they're grouped in the subsets called clusters. And we start with the initial cluster, and we can mutate to get different clusters. In particular, in this case, we start with a polygon and we triangulate it. And initial triangulation, just like in SR-Sof, it gives us our initial variables. And if we want, we can also name the boundary or just leave them as one. And let's say we want to understand another triangulation. We can try to describe this X4 in terms of our first three variables. And for that, we can use the Ptolemy relation. So in this case, this gives x1 times x4 is equal to b1 x2 plus b2 b6. So we can rewrite x4 as this fraction. And now this tree becomes our new triangulation. So this is the same thing as I was describing before in terms of mutations. There, the difference was taking these boundaries as one. So this is how it would look like if the boundaries are not, they don't have names. They would look slightly more involved if you also take the boundaries into account. And the thing we are working on is, if you take any curve here, you can do the mutations again and again and use the Ptolemy relations, and you can eventually get an expression for this. For this one, the expression would look like this. So if you need more mutations, you get more terms, so it does sort of get longer as you get a lot of crossings. But there are also ways of doing it more directly. There is the snake graph method, and there is also the poset method. So in the poset method, you turn this shape into a weighted poset. And it is very similar to the examples we did in other talks. If these are the first ones, x1, x2, and x3, you pick a direction to orient inner triangles. So you can pick clockwise. And add arrows. And you get a poset. If you say, okay, the pointing direction is going to be up in the poset. And then you get labels by adding looking at clockwise neighbors and counterclockwise neighbors. So this was something we did before. And what you can do is, you can calculate this weight polynomial of this poset and plug in these labels. And this gives you the cluster variable when you multiply it with a constant. So you, like this one is the main one that gives you the list of the terms, and then there's an initial term, you multiply it. And the method of calculating these weight polynomials is something that I call oriented posets. So this works with just for any poset, you choose some connection vertices and you associate them with matrices, so that multiplying matrices gives this inclusion-exclusion relation. So this is just a way of speeding up the combinatorial process. But for our particular case, we just have two building blocks and two matrices corresponding to them, the down and up matrix. And if you want to build up any poset, for example, this poset, you can divide it up into their nodes. So this is one up, one down, and we always end it down as a convention. So if you want this poset, you can multiply the up matrix for W1, down matrix for W2, and down for W3. And that gives you the matrix for this completed one. In particular, you can read the weight polynomial from the top left entry. So you can do it for even bigger posets. And it's pretty practical, especially if you are trying to do calculations by a computer and like check different versions. Like this is very fast. Which brings me to the actual topic at hand. This is mostly based on the new work we have been doing with Emine. It is almost a preprint, but it's not up yet. We hope that will be up in the next month or so. Like it's, here we are working with super close algebras. So in this method, we have all the structure we had before, but we have some extras. Each triangle also has their own variable. And these ones are no longer commutative, they super commute. So you have theta I, theta j equals minus theta j, theta I. So we have minus signs. And they're also nilpotent, so if you multiply it with itself, you get 0. So this is a bit trickier if you want to do commuters with it because of these two properties. But we were looking at it naively. And for these, you can also do the same mutations. And you get the super manipulation. And if you get rid of these terms, you will recover the old one. So if we don't look at the extra variables, you still have the same structure. Now you have some extras. But now because triangles are also variables, he might be interested in the expansions of the triangles in terms of the initial triangles and variables as well. So there are these extra relations that are added into the picture. So it is both very similar and more complicated than the structure we had, because now we have to keep track of more stuff. But the basic notation works the same way. So it makes sense that a very similar combinatorial structure should do the job. But we have to be careful about the minus signs. We have to be careful about the idempotent elements and so on. So we were asking ourselves, okay, can we do the similar calculations in the super case? For example, if we take the super envelope of the same curve we had, can we do the calculations for that one with posets? So in this case, we have the two-row versions of the same posets. And naively, this model does the job. So if you look at the weight polynomial of this poset and you plug in these variables, it's sort of okay, but there are some little issues. I don't know if any of you can spot any issues. I think Francesca did when we first talked about it to her in Bamford, said, "What are you doing here? Like you cannot divide by that. That's these are idempotent, so this could turn into a zero division." So that's a slight problem. And then there's the thing about the whole structure of these poset ideals was commutative. And we didn't put any sort of ordering on these. And now we are working in a non-commutative picture. So two big issues at this point. That this model, even though it gives us what we want, doesn't technically work, but we can do some cheating. So there are two things we do. One was also done in the other papers working on this. And it's sort of way to get rid of the minus signs. You define a positive ordering on these new variables, and you always write them in that positive ordering. And that can help you have a picture without the minus signs. If you give the right sort of ordering, you don't really have to worry about them. But there are also these divisions. And for that, we just say, okay, we are not actually multiplying. It was what we told Francesca when we just thought about it and said, okay, we are changing what we are doing. We are not multiplying. We are just doing an operation of adding this variable or removing it. Which does sound like division, but it is not division. It is just removing something from the multiplication, which we could technically do. And because of these relations, actually, to have this one, you have to have the one before it. So to be able to divide by theta 1, you have to have theta 1 in the term. So you do not have these negative signs actually. You are just removing terms. So our new operator, what it does is, it looks at each monomial. It says, if theta I isn't there, I'll add it with respect to the positive ordering. If it is there, I'll remove it with respect to the positive ordering. So now our picture turned into this. And this, these operations, they are idempotents. So they are nicer to work with. We don't have the zero division anymore. And we also have an extra advantage. The labels started to match for these vertical pairs. And that means the combinatorics is going to be easier because for this picture, we don't need 6 weights, we only need 3 weights. So with that, we were able to give the analog of our theorem for the super case. This is the new one. The one for the arc is the same. What changed is the posets changed. And we also have these formulas for the neighboring triangles. They are a bit more complicated, but like we have some additional terms to multiply with, but the main term comes from the same poset in each case. These are some subsets of the ideals. And by these neighboring triangles, these are what we mean. So it generally makes sense to describe like if we are looking at this curve, we also with the same poset, we can calculate the triangles that come from so one does come from I plus 1, 0 triangle, and the other is the I minus 1, 0 triangle. Well, this is nice. You're up here. But the goal is also to give a nice matrix model for this thing, because the combinatorial we did the combinatorial poset model for the classical case too, and there are also other models for that. There's a snake graph model. There is also the snake graph model for this. The main advantage of the poset model is the matrix calculations that come with it, so that we can say it is simpler. And for this particular model, there is also a matrix version, but the existing matrix version is a lot more involved. So we were hoping like this will be, if we can make it fast, it will be useful as a shortcut for people working on that. So this combinatorial expansion, this I'm working on this with an undergraduate student of mine, Mark together. And I'm just going to tell you about the parts related to these posets in general. And it is a very simple expansion. So instead of this up step and down step, we have a double up step and double down step. Names might change. And they have their matrices, but combinatorially it works the same way. So now your building blocks are shaped like this. And instead of doing up, down, and down, you do the double up, double down, and double down. And again, you multiply the matrices, you get the matrix for this larger posset. And how it looks is like this, like it is a longer matrix because we get more terms, but the full posets that we are looking for, it again comes up in the top left corner. So in practice, we just change the matrices, everything works pretty much in the same way. And if we also get this zero t path, like that's the term doesn't change when we are moving into the supersetting. We just multiply it and then put the labels and get the expansion. We offset these extra formulas. You can also get these pieces from the matrices because I didn't talk much about it, but there is a combinatorial description for each entry. So if we are looking for this polynomial, you take the sum of these two terms on the top row. And if you are looking for this polynomial, you take the sum of these two terms, but then multiply with a minus sign because these are both negative. And you can also get these by multiplying with the extras. So how it works in practices. This is an even simpler example, so I think the matrix will fit for this one. So here we have two crossings. So we just have the one step matrix, the 4 element matrix, the 4 element poset here. And we get the weights from the triangulations. These come from clockwise and counterclockwise neighbors. And the T1 and T2 comes from, like, this is X1. The neighbors are θ1 and θ2, so it gets T1 and T2. And for this one, the neighbors are θ2 and θ3. So we get, not T right, actually tau in ring. So we just say, okay, you can think of this as an up step and a down step. And then we get a top plate coordinates. This gives us the weight polynomial. And the polynomial looks like this. Because it's the simple poset, the polynomial is on the simpler side. And we plug in the weights. It's no longer looks as nice, but this is the flavor of the solution we are looking for, so nothing to do there. And we multiply with this initial variable, and then we evaluate these toggle operations, which basically means just turning them into theta's. And we get our solution, and we could do the similar thing for the triangles as well. And, okay, 25 minutes. I do talk fast, and this was an extra of how these posets work in general. You pick a pair of target vertices and a pair of source vertices, and you can define these connection matrices combinatorially by adding some conditions on which ideals you are looking for. And they work nicely. You can multiply them to combine posets, or you can take the trace to combine two ends of the same poset to close it up. And this is basically it. If you are interested in cluster algebras and this was only into you, like there are many sources. Perhaps Schiffler's lecture notes from a simple school are a pretty good source in my opinion. And for the super spaces, there are many papers, but they are generally from the last 5 years. So this is one of them, but you could probably read all of them in a sort of like, there are 5, 6 of them, so you can know everything about that if you are interested. So these are the works that I talk about in this talk. This is the one with Emine. It's about the superclass expansions and how we do it with these posets and matrices. And this is with my students where we just look at the combinatorics of it and how would we work with these posets in general if we are not particularly interested in cluster algebras. And these are the slightly older ones. This is where I defined oriented posets combinatorially. And this is where we apply them to cluster expansions with Emine.
Thank you so much. So let's jump time for questions.
Yes.
Questions or comments?
In your, so the first row you used to get the arc and the two triangles. What do the other rows in your paper start after?
So, okay. For we think of this combination operations as just adding stuff, I guess, from the right. But you could, it is a symmetric thing, so you could add stuff from the other side too. So these other rows have conditions that are tied to these target vertices. So that when you are trying to connect the two of them, the columns keep track of information about these. The rows keep information about these. And the column row connection does this interrelating thing, which takes care of the inclusion-exclusion aspect of it. So, because we generally work with, okay, I think the picture might be more helpful, but yes, because we generally perturb this end, we only are interested in the row. Technically, the column will be just changing this end and looking at this pair of triangles, like I and this dot and this one and that one. Like you can get this one, and if you move both points, so if you are looking at a triangle like this, then you could look at the other entries of the matrix. So they have a combinatoric reason of being there, but in terms of cluster algebras, it will be moving the other end.
And you know how to toggle and stuff.
Yes. We added two comments like in case people want to use those formulas as well, because it might come in handy, but it is not very, very useful because you could also flip the arc and then move it through.
So I learned a lot about cone matrices from one of your earlier papers. Have you ever thought about doing higher dimensional? I mean, with these double up, double down, or whatever. Have you ever thought about a higher dimensional cone matrix?
The matrices, like in the paper, we are working with like
Not
any
the
like
case. I just meant you have this thing for the double up, double down.
yes, like the paper with bar in the paper with bar two, we are not looking at the double up, double bars. We are looking at lines of general size, and you can connect different lines. Like one of the motivations of looking at these was to describe young tableau diagrams like that. Because they can also, they also have the posset structure, and for that, you can start with the middle piece and you add lines of different sizes. From both sides. So in this particular project, we work with ROMs of 2, but the commuters, they're a lot more in a more general sense.
Is you using like non-square matrices?
So it depends on the number of connections you have. You always use square matrices, but if you have like k connections, you would need a k plus 1 times k plus 1 matrix. But you can connect different sizes as well by taking 0 rows. And
Oh, okay.
there's a lot of playing around you can do. And if we wanted to do a cluster expansion with 3 rows, like we could do the combinatorics, but I don't think the algebra is there. So we are looking for like what would it mean algebraically if you work with 3 rows or 4 rows. Just like the combinatorics, it's very easy to alter into different settings.
Any other question or comment? If not, you can speak again. I'd like to mention